Hi, this unit is going to be on bootstrapping. And I'm going to start with the history of the word bootstrapping. Where does the word bootstrapping come from? It refers to pulling yourself up by your bootstraps. So that's an old expression. But it goes back to the beginning of computer science. So in the beginning, an assembler, programs were written in binary. You would toggle little switches to toggle in a program in binary. And then somebody wrote an assembler that they wrote in binary, they wrote an assembler that could assemble more symbolic machine code instructions. And then at some point, a Fortran interpreter was written in assembler, which is a friendlier language. And then once you have a Fortran interpreter, you can write a Fortran compiler in Fortran. So you're bootstrapping, you're taking the tools you're building and using them to build the next tool. And this history is a little bit of a joke, but this Fortran compiler written in Fortran is circa 1960. And as far as I know, we're still writing C compilers in C. But this progression, has always led to the question whether we will eventually just be able to write programs in informal English and have the computer program them. And I want to read this quote from I.J. Good, 1969. So this was near the dawn of computer science. Let an ultra-intelligent machine be defined as a machine that can far surpass all the intellectual activities of any person, however clever. Since the design of machines is one of these intellectual activities, an ultra-intelligent machine could design even better machines. There would then unquestionably be an intelligence explosion, and the intelligence of humanity would be left far behind. Thus, the first ultra-intelligent machine is the last invention that humanity need ever make, provided that the machine is docile enough to tell us how to keep it under control. So this is, a very early expression of something that people have been talking about a lot lately, in terms of the possibility of AGI. But I want to think about this issue of bootstrapping and languages getting more friendly and more sophisticated. And is that related, is the evolution of programming languages, because after all, programming languages are sort of the most expressive, most powerful way of representing functions. Is the idea of a high-level programming language, or is a high-level programming language like Python expressing some kind of bias about knowledge representation or a representation generally that is effective as a learning or thinking bias? And it does seem to be true that high-level languages greatly increase the productivity of human programmers. And if we're ever going to get to this intelligence explosion, presumably these high-level programming languages are relevant or significant, or will be relevant or significant in our understanding of how to get computers to take over the process of designing themselves. In the programming languages community, people talk about the Turing tar pit. So it's very difficult to do the theory of programming languages or the theory of programming languages is inhibited by the fact that any two programming languages, say Python and assembler, are both Turing complete. You can do anything in assembler that you can do in Python. It just might be more painful. And this is related to our free lunch theorem, right? If we talk about the number of bits it takes to write a program, you might think that an assembler program is going to be much longer than a Python program. But that's not actually provably true. In fact, what you can do is if I want to write things in assembler, I can bootstrap, right? The first thing I can write in assembler is an interpreter for Python. And then if I want to write something in assembler, I simply pass a Python program as input to the Python interpreter. So if I take that approach, if I bootstrap within the assembly programming language, if I bootstrap by writing a Python interpreter there, then if I've got a target function I want to represent, h, the number of bits it takes to represent that in assembler, I'm going to talk about this is the number of bits it takes to represent it in Python plus the number of bits it takes to write the assembler. So that means that for any function, the number of bits it takes to represent that function just has an additive constant relative to assembler. So there's this sense in which all programming languages are equivalent, and that's the Turing tar pit. And I've just said this. So we've said that the fundamental problem is the search problem. It's quite possible that searching for Python programs, coming up with a Python program, is a lot easier than coming up with the assembler program. But this problem of searching over programs is related to something called Levin's search. So now we're going back to sort of the middle 20th century, 1973. And Leonard Levin proved this, if you say it the right way, it's kind of shocking. He proved this theorem that for any problem in NP, so Boolean satisfiability, any problem that has a non-deterministic polynomial solution, if there exists a polynomial time solution, let me put it a different way. There exists a universal program that will take as input a solution tester. So I've got Boolean satisfiability. It's easy to write something that tests whether an assignment satisfies the formula. So there exists a universal interpreter which will take as input a tester. And if there exists a polynomial time program to find something that satisfies the test for finding the assignment, this universal interpreter will run in polynomial time. And you can even say what this interpreter is, right? So this sounds shocking. So I hope I said that clearly enough. And it's a little bit more general than that. That anytime there exists a universal interpreter that you pass it a tester to test if something's a solution, and it will run only a constant factor slower than the best algorithm for finding solutions to that problem. And the proof is kind of trivial and shows that the theorem's not very exciting. That happens with a lot of these very general universal statements. It ends up being kind of trivial and not very exciting. What we're going to do is we're going to timeshare all programs. There's a countably infinite number of programs. I can define a time-sharing system that assigns some finite time slice to every single program. In fact, I can define a time slice 2 to the minus length of the program. So 2 to the minus length of the program sums up to 1 over all programs, or sums up to something less than 1. And then if I timeshare them all in parallel, then for any program H, you're running a constant factor slower than H itself. That's a whopping constant factor, but it's only a constant factor slower than running H itself. So if there exists a polynomial time H, you're running only a constant factor slower, so you're running in polynomial time. So Levin's search time shares all possible programs. So this is another warning. If you encounter this Levin search thing, alarm bells should go off. Bootstrapping. Bootstrapping the search. So this is an interesting observation that Hinton and Steve Nolan made quite a long time ago, 1987. And they pointed out a paper from 1896 about evolution by Baldwin. So this is called the Baldwin Effect. So this is about evolution, and it's saying that learning, adaptivity, learning, facilitates evolution. So to think about this, suppose you're evolving a body form and your body shape and your legs want to evolve. You want to run faster or become bipedal or something. If your motor control system is a learning algorithm that can learn to control any actuators, any arms and legs, then as the arms and legs themselves evolve, the learning algorithm can just deal, right? So it means the evolution doesn't require simultaneous evolution of the legs and the controller. The controller can handle any legs. That's going to make evolution a lot easier. So learning facilitates evolution. So I'm going to introduce this phrase Metabaldwin. So the first observation is that this should apply to brain structures, right? If I've got a bunch of modules, you know, I've got something that does vision, I've got something that does motor control, and these are modules within the brain. And if the brain modules can learn how to interact with the other brain modules, so each brain module is learning how to interact with the other, then you get this kind of independence in the brain modules also. One brain module can evolve and the other can just deal with that evolution. And then there's this sort of vague intuition that this should apply to modules within learning also. So this Baldwin effect should facilitate the evolution of learning. So can we bootstrap learning? So bootstrapping, so the fundamental problem here is this problem of finding the functions in our programming language, finding the Pythons or some representation of the function that we're trying to learn. And Schmidhuber, the well-known Schmidhuber, one of the four horsemen of deep learning, proposed a learning algorithm that he calls the optimal ordered problem solver. And this goes back to 2002. And the basic idea is sort of like the Metabaldwin effect. And it sort of combines the Metabaldwin effect with Levin's search. So he's going to search over all programs, but one of the programs he's searching over is the program that searches over programs. So he's searching for the most effective search over programs. And you can prove a theorem that that this thing, given enough time, would find the optimal, or given the right time slice for the right program, is going to run a constant factor slower than the optimal search algorithm. But again, you've got this time sharing at the beginning. You've got this time sharing over all programs that just in practice kills it. So this is not a practical thing, but you might encounter this idea also. This because Schmidhuber really pushed this and still really pushes this. Okay. So now we're going to move on to logic in the next unit. And there's lots we're going to say about that.